Okay, in this video I'm going to continue on with my solution using the Frobenius method to the differential equation written in green. This is part 2 of the solution, so this is clearly a direct continuation to part 1. So in part 1 what we did was we got the second and first derivatives of the power series and we multiplied where appropriate by x squared and x, and we plugged them into the power series and rearranged. We got two equations, equation 1 and equation 2. Now where this contrasts with the normal solution using power series is that in usual solutions for power series we get a single equation like so, and in that we're able to get our recurrence relation. However, because in the power series we have an extra factor of r in the power, basically we get a second equation here which we call the indicial equation, like so. So what we need to do is solve the indicial equation and then solve for our recurrence relation. So if we look at our indicial equation here, immediately we see that there is a common factor of a0 times x to the r. So if I take that out, we're left with r squared minus r plus r minus 1 is equal to 0, and r is equal to plus or minus 1, like so. So that gives us two separate values for our indice r, which will affect our solutions to the equation. The next thing we're going to do is solve equation 1 in order to get our recurrence relation. Now I'm just going to factorize it out immediately, and we're going to get the following. We're going to get an plus 1 outside of n plus r plus 1 times n plus r plus n plus r plus 1 minus 1 is equal to an times n plus r. So I'm just going to divide immediately by n plus r here. Alright, now what we really want to do is get this here to have an n plus r in it as well. And the easiest way to do that is to factorize it as follows. So we're going to still have an plus 1 on the outside, and we're going to have n plus r here. And if we do that, we're going to have n plus r plus 1 from here, and we're going to have a plus 1, an additional plus 1, like so. Alright, and that's equal to an. So therefore, as a result, we're going to get an plus 1 is equal to an, and that should be closed like that, an over n plus r plus 2. And this is our recurrence relation. And I think I've spelled that right. If I haven't, I don't really mind. But of course we know at this stage that we have two values for our indice r, plus or minus 1. So as a result we'll actually have two different recurrence relations. We'll have the recurrence relation for r is equal to minus 1, which says that an plus 1 is equal to an over n plus 1, and we'll have the recurrence relation for r is equal to positive 1, and that's going to be an plus 1 is equal to an over n plus 3. Alright, that's pretty straightforward stuff. So from here on, it's the procedure is the exact same as your normal power series solutions. So what we'll do is we'll plug different values for n into this, and we'll look for a pattern. We'll plug different values for n into this and look for a pattern, and eventually we'll have two independent solutions. So this will give us y1 and this will give us y2. These are two particular solutions, and that y general will be equal to the sum of the particular solutions, like so. Alright, so I'm just going to clear out this board here and begin doing that. I'll be pretty quick because it's reasonably straightforward stuff. Alright. So what I'm going to do first is go for r is equal to negative 1, whereby our recurrence relation says an plus 1 is equal to an over n plus 1. So for n is equal to 0, we're going to find that a1 is equal to a0 over 1. For n is equal to 1, we'll find that a2 is equal to a1 over 2. However, we already know what a1 is, so let's plug that straight in. We're going to find that it's a0 over 2, and we can now see that there are factorials involved in this. N is equal to 2. We're going to get that a3 is equal to a2 over 3 is equal to, and we can plug, we have, a2, which is a0 over 2 factorial, and now we're going to get a0 over 3 factorial. Remember, factorials will say 3 factorial is equal to 3 times 2 times 1. Alright? And I suppose if you look at this, if you look at it hard, and it's a small bit of a knack to it, and I won't put too much of an emphasis on it. You either get it or you don't, it's not too important. You're going to find that an is equal to a0 over n factorial. Alright, so what we can say is, we can also say, however, because we defined at the very start that y is equal to the sum from n is equal to 0 to infinity of an times x to the n plus r. That's what our power series is. And what we're after finding out is our ans. So, for example, we're going to find that y is equal to, we'll say, a0 x to the n. Now, r in this case is -1, so it's n minus 1. And it's going to be plus a1 x to the n minus 1. Yeah, that's right, isn't it? a0 plus a1, but 1 minus 1 here, like that, plus a2 x to the 2 minus 1, and so on. And we know our value of an now as a result of that. So the last thing I'm going to say here is that the first solution, y1 of x, is equal to a0 times the sum from n is equal to 0 to infinity of x to the n minus 1 over n factorial. That is our particular solution, y1. And that's very straightforward stuff. So let's just do our particular solution, y2. Okay, particular solution, y2. So in this case we're told, or we're not told, we found out, excuse me, that an plus 1 is equal to an over n plus 3, whereby r is equal to positive 1. As a result, do the same thing, start plugging in your values. For n is equal to 0, you're going to find that a1 is equal to a0 over 3. You're going to find that for n is equal to 1, that a2 is equal to a0 over 4 times 3. And that's going to be equal to 2a0 over 4 factorial. N is equal to 2, you're going to find that a3 is equal to a2 over 5, and that's going to be equal to 2 times a0 over 5 factorial. When you just plug in we'll say the values of all you've already worked out. So it's now time to start looking for a general answer, and we're going to find that an is equal to 2 times a0 over n factorial. Alright, 2 times a0 over n factorial. So as a result of that, when you plug in your, you do your power series, we know of course that y is equal to the sum of an x to the n plus r. You're going to find that y2 of x is equal to 2 times a0 times the sum of n is equal to 0 to infinity of x to the n plus 1 over n plus 2 factorial. And that's actually n plus 2. Excuse me, what am I doing here? That was n plus 2. Okay, the reason it's n plus 2, because if you look for the third term we're at 5, the second term we're at 4. Okay, so it's n plus 2 factorial. Alright, and as a result, we see that we have two linearly independent solutions. I'm not going to go into why they're linearly independent, but that's what they are. So we know that ygen, the general solution, is equal to y1 of x plus y2 of x. That's how you solve that particular differential equation using the method of Frobenius. So if that was pretty straightforward, if it wasn't, please ask me some questions. Thanks for watching, please pass it on to your friends and subscribe to my channel.